Yeah, good morning, everybody. My talk is on multi-sensor investigation of upwelling, including Sentinel-1 SAR data. So I will focus very much in this talk on SAR data. Now, so in studies of remote sensing of upwelling, usually optical and infrared data are used. And so optical data, from them you can get ocean color, and from ocean color you can get the chlorophyll concentration out of it. And the sensors that are mostly used for this are the MODIS sensor, which are on Aqua and Terra, but one is dead now, and on Landsat the OLI, and this is what it is doing. And infrared, from that you can get then the sea surface temperature out. And there are many sensors flying, and the data from these infrared sensors, they are combined to then obtain the sea surface temperature. And one of the most used sensor is MODIS and VIRS. And now there are these Sentinel sensors. So here for chlorophyll, that is just a second. Where is it now? No, this way. You better use this. Okay, yes. Okay, so now we have the OLCI sensor on Sentinel-3. There are two Sentinels flying right now, and so they are very good with high resolution to retrieve then the chlorophyll distribution. And on Sentinel-3A and B are also an SST sensor, which has also a high resolution. So now, and also synthetic aperture radar is also a very nice sensor to study the upwelling. And now, why can you use SAR for studying upwelling? Upwelling regions become detectable by SAR because they are associated with a reduction of the stability of the air-sea interface. That is a smaller effect, but the bigger effect is through a damping of the short waves, the break waves, by the presence of biogenic or anthropogenic slicks under light wind conditions. And so usually coming to the stability here, usually the air-sea interface is neutrally stable, so the water and the sea surface at the sea surface and the air, they have the same temperature, then it's neutrally stable. But when the water is cooler, then you get a more stable stratification. And this then reduces the radar backscattering or the normalized radar backscattering. And also upwelling regions become sometimes visible by convergent regimes at the rim or of the boundary. So upwelling then encounters the ambient water, and then you get a front there, and this front is associated with convergent flow at the sea surface. And here is just an example of SST image or map and a chlorophyll A map from MODIS. And you see here in the first image the SST. This is here the west coast of South Africa. Here is Cape Town here, you can see it here. And there is wind, the trade wind blowing from south to the north. And we are on the in the southern hemisphere, so the Coriolis force acts in this direction, and you get then upwelling, and this area is very well known for upwelling and the high biological activity that then implies that you have a lot of fish there. So that is a very prominent fishing area. And so this image was taken 3 days later than the SST image. Usually there is a small gap, time gap between the upwelling and then you get plankton bloom with a delay often of 1 or 2 days. And you see here that the boundary of the upwelling region is not too homogeneous. You get here patches of cold water, and here then you get increased upwelling. This then causes increased plankton growth, and you see here this is we see a pattern that is cyclonic. So in the southern hemisphere it is rotating a clockwise direction. And now we come to the SAR image, which was acquired almost at the same time, so on May 2nd of May. And so this is a typical image of an upwelling area. And so you see here an area A and then an area B. They have on the average here a different brightness, so different normalized radar cross-section, but it's very inhomogeneous. But on the average, you can see that this area is somewhat darker, so has a lower backscattering than this, due to the change of the stability of the air-sea interface. And now you also can see here a bright line that is a boundary between these two areas, and you get then upwelling, and this upwelled water then encounters the ambient water, and you get a convergent flow there that then causes increase in the radar backscattering. And so then you see here this cyclonic eddy, which becomes visible by the presence of surface films. So when you have plankton growth, then the living material in the area that exudates surface active material that float on the sea surface that are usually form a monomolecular layer. And these surface films, although they are only monomolecular, they have a very strong effect on the damping of the short waves, as strongly as do mineral oil films. So it is very difficult to distinguish between these very, very thin biogenic surface films and thicker oil films, mineral oil films built by tankers or so, because they give a comparable reduction in the radar cross-section. So in this case, the reduction of the radar cross-section is about 10 dB, and if you look at the reduction between area B, in this case, it is only half a dB. And now, according to weak hydrodynamic interaction theory, the gradient of the sea surface current can be inferred from the variation of the radar cross-section across these fronts. So this is an old theory, so more than 30 years old. It is weak hydrodynamic interaction theory, so it describes the variation of the Bragg waves that are responsible for the radar backscattering by a variable current. So you have convergent and divergent regimes, and in this simple theory, then the relative change of the radar backscattering or the normalized radar cross-section is related to the gradient of the surface current in look direction of the antenna. And there is a factor in front that is the relaxation rate, which is dependent on wind speed and often not very well known. So in this case, if you have weak changes in the surface current field, then you can use this theory. If you have stronger convergence and divergence in the current field, then often wave breaking occurs, and Mr. P. Bayev, he has just explained in the first presentation. So there is an improvement now of this theory, including also wave breaking. And Kuryatsev from St. Petersburg, he is one of the leading person who has developed an improved theory, interaction of radar, no, interaction of the modulation of the radar backscattering through varying surface current. Now I just give you some examples where you can see that, and first of all I show some SST and chlorophyll A images, and then a synthetic aperture radar image of the return current of the Agulhas return current. So as you know, here you have South Africa. The famous Agulhas current runs southward along the shelf, and then part of the water ends up in the Atlantic, but part of the water then travels eastward as Agulhas return current. And so you see here now and from a model, the geostrophic surface current streamlines. So you have here the Agulhas current, and then the return current, and often meanders happen, and you get here then a cyclonic meander. This would then imply that you get upwelling here, so cold water comes up. And in the SAR image now, acquired on the same day, you see here the feature, very little decrease here in the center of the radar backscattering, but you see very nicely here the front where these two water masses meet, and you get then a convergent flow. And here you see the SST image from the same day, or almost the same day. And so this cyclonic meander generates here cold water, and then in the chlorophyll map you see that at the rim there is an increase in the chlorophyll concentration, and maybe I focus again on this SAR image, where so we made here a scan through this feature here, and indeed here the increase of the radar cross-section across the front was about 2 dB, and also here, and you see that here in this area, so the radar looks in this direction here, and you get then no modulation here. Yeah, it could be partly due to the slicks here, but nevertheless, so the radar signature is very much dependent on azimuth angle, so the angle so the angle between the radar look direction and the surface gradient. And you can see here also some detailed features, so maybe that there is some secondary front present. And now I just want to show you an example from upwelling along the east coast, east and southeast coast of Sicily. So this is ongoing work, and we have not yet completed that, but I think very nice features appear there that you can see on SAR images. And here now upwelling occurs at the front of Sicily. So here is Italy. This is Sicily in the Mediterranean Sea, belongs to Italy. And you can see here that the bathymetry is very variable in that area. So you have a shelf. This is a 100-meter line, and you get a plateau here. So, and the upwelling occurs here. So you have in summer and in autumn, you often have a very strong wind blowing along here this coast line, and then you get upwelling. And in the next view graph, I show the statistics of upwelling in 2070. Here you have the wind. So upwelling occurs at this in this area only in between May and October. And here you have 9 upwelling events. So plotted is here in the black curve. It is the SST averaged over a region at the southeast coast of Sicily, and you can see that you get wind bursts here. I think 9 in this year only, so 9 times you have these, in this year you had these upwelling events, and then you measure the SST. In this case, MODIS images were used, and you can see that there is a fluctuation in the SST, and a decrease in the SST occurs just a little bit later than the wind burst. So it's a delay of 1, 2, or sometimes 3 days. So this you can see really nicely increase in the, oh, that's not the wind speed, it's the wind stress. So the wind stress is a wind speed, but taking account or correcting also for the stability of the air-sea interface. So, and so you see here nicely these correlation between the increase in wind stress and the decrease in the sea surface temperature. And here is an example of a wind. So this was taken from Internet Night School. It's a nice website for getting so the wind here, and you see here Sicily, and here wind at that time was 8.3 meters per second, and this wind usually, or very often, originates from the Rhone Delta. There is a famous wind which is called Mistral. Oh, the L is missing here. Okay, but the L then is here. Okay, so this is an example, and now on that day or one day later, you get here with Sicily, you get then here an increase, a decrease of the SST. That are data from sea, land, surface temperature radiometer, so of the Sentinel. And now then you get from the same Sentinel then the chlorophyll concentration by the ocean color sensor OLI on that. And you see here then this increase in the chlorophyll concentration, which forms here so-called filament. So it is not only here at the on the shelf, but in this case the wind was not coming so much from the south, from the southwest, but more from the north. So you get this kind of feature there. And now here in this area, there you will get an eddy which becomes visible by the surface slicks. And this is the Sentinel image of this area. And here you see areas of reduced radar cross-section, so caused by the presence of surface slicks, very likely of biogenic origin. And if you do a zoom, then you can see here this cyclonic eddy, which becomes visible by the entrainment of surface films in this surface current field. And I will then show you another example 1 month later in this area. And you have here again upwelling visible in the sea surface temperature map. And then you have then chlorophyll concentration, and you get these kind of filaments. They have been studied before a little bit, but not really systematically. So they evolve in the decaying stage of an upwelling event. Then they develop, and they usually they even form, as you can see here, cyclonic features. And the images I showed you before, they were from MODIS, and now we have them from Sentinel-1 SAR. And you see, I think, here now more details. So I really urge you, I think on the first day somebody who talked about forest remote sensing, that here in Russia you are used only to American data, to MODIS data, and you don't use so much European data. So I want to make a commercial on that to use them. And you can see here even now here these features in much more detail than, or in better detail than on the MODIS images. And now here is a Sentinel-1 A image taken at the same time, or almost at the same time. What was it now? Okay, yeah, 28th, yeah, so 2 days later. And you see here also areas of reduced radar cross-section due to upwelling, but not caused by the change of the stability of the air-sea interface, but due to the presence of slicks. And now I will zoom on A and B, and here you then see these nice features of cyclonic eddies here, and also here. And what is noteworthy, actually, that is in a recent paper by Victor Surbas here from the Kirchhoff Institute. Often you have here line features already pre-existing, and if you have line features here, you know, then they are captured by this one. So this is a line feature, and then it joins this eddy. And now I return, I go to another feature that is often associated with upwelling. These are internal waves. And again, here the image of SST image, yeah, obtained from this website. In this SST image enter data from several infrared sensors, and you can see here that there is upwelling that occurs mainly here, and that it is then transported somehow further south. And now here is the Sentinel OLI-TIRS map showing the chlorophyll concentration, and you can see here that this feature, that there are cyclonic features that evolve, and so this is the corresponding Sentinel-1 image, and you can see here that you get surface slick coverage, and that follows quite a bit, or quite well, the feature you saw here in the chlorophyll map. You see here, yeah, so here, and so there is a correspondence, but not 100% correspondence. The slicks, they, when they are generated, they can move and so on, so they don't stay on their place of origin. And now here we have some internal waves that are generated in this area here, which are mounted here. And these internal waves, they have quite different shapes, and it is, yeah, and they have here, if you make a scan through this feature, you get here this radar cross-section variation, which can be described by weak hydrodynamic interaction theory. And then also here we made a scan. So you can work with them. And now I show my last example of upwelling that occurred 1 month later, or on this day. And here again the SST image and the chlorophyll image. And again you see these filaments, yeah, they then evolve into cyclonic features. And also the Atlantic-Ionian stream matters. So here, due to the wind, you get this. Yeah, this is so the stream, or the water, comes from the Atlantic and bends around here. So this also matters. And now I have the Sentinel image, and I look here at this area where you have increased upwelling in this case, mainly due to the northerly wind. And so here you see then the internal wave field, and this you don't not only see on one day, but you see it very often on in this area. So this is another day, and you can see that these waves have quite different shapes, and it is not easy to identify where they come from. So they are here in surface film, in areas where you have surface films. So the radar signature of internal waves is here different. In the convergent regimes, you get an accumulation of slicks. And now this is another image on another day again. So you see all kinds of internal waves that are generated. And now the hypothesis is that these internal waves are caused by upwelling. Actually, I have checked the archive, and I only found these internal waves during upwelling events, so that is not so much a hypothesis anymore. But now the question is, what does the bottom topography to it? Does it have an effect on the generation? And there is also then change in the mixed layer depth. This is a mixed, so this is Sicily here, and you see here the east coast, and the depth of the mixed layer that come from a project that is run in France mainly. So the no, not in France, in Italy. Nadia Pinardi, she is from Italy, so she has developed it. And so you see that here the depth of the mixed layer is very low, of the order of only 5 meters. And it follows then the upwelling areas. So, so much to these images. And now people, they want they put now much effort in modeling small-scale oceanic phenomena using high-resolution oceanic models. And now my last slide shows an example of modeling that Victor Surbas has carried out, and also Olga Rovak is participating in these modeling efforts. And so Victor Surbas, whom I will meet besides the day after tomorrow, and maybe we collaborate on these things then. And so he has mainly worked on modeling upwelling events in the Baltic Sea together with scientists from Tallinn, and they have found that there are often eddies are generated that can be detected in ocean color images. So in this case of a MODIS image, but I think it is not not transformed into a chlorophyll A map. But you can see here these cyclonic eddies, and here not so where, yeah, and here is an anticyclonic eddy here, so that forms a dipole. And he is able, by using a very high resolution oceanic circulation model, which is available publicly from the United States, I think from the Giovanni website or so, and you can download that and adapt it to your purposes. And so this is a modulation. So to speak, this image was modulated, and he is able to predict or to hindcast the surface current field. And now what he has done, he has put into a model particles on the sea surface, equally distributed, maybe several thousand particles. They are floating on the sea surface, so they mimic, so to speak, then surface films that then follow these current features, follow the current field. And you can see here that indeed here these observed eddy structures, they are well modeled, and that is really a surprise. I showed it just to people in my institute, and so so they almost couldn't believe it, that by a model, by a high resolution model, and including an estuarine model, so you have to include as an input the outflow of the rivers, of the 10 or 15 rivers you have then, and you have to use as an input, of course, then the wind history, and then you have it run the model, let's say, for a week or a month, and then you get a redistribution of these floating particles by a Lagrangian method, you see, and then you get that. So, and this is of a great value for oceanographers, and so these phenomena, these small-scale phenomena, play a key role in upper ocean dynamics, and their modeling has has recently started using these high-resolution models. So they have a resolution of maybe 200 meters and so on. And this is a very, very hot issue now in oceanography. And here I just have shown that in addition to SST and chlorophyll images, also synthetic aperture radar images are useful for studying upwelling events, small-scale eddies, filaments, and internal waves. And that's all, and thank you for your attention. Спасибо.
Thank you, Professor Alpers.